Well, hello everybody. Welcome to week 7 of Probability and Statistics. This week, the first lecture is going to be just one part, and we're talking about one of the most common continuous distributions that we are going to discuss, which is the normal distribution. The normal is probably the most popular because of something called the central limit theorem. And we're going to also talk about that this morning as well. So without any further ado, let's take a look at our slides. As I mentioned, the normal distribution is a very popular distribution. I'm sure you've all seen it before, the familiar bell-shaped curve. And basically it's popular because sums of random variables tend to the normal distribution by something called the central limit theorem. And we'll discuss that theorem a little bit more shortly. The actual distribution of the normal is a fairly complicated looking expression that involves a squared x term. The main things to note about the normal distribution is the range is from minus infinity to plus infinity. So we know in fact that the normal is not a good distribution for a lot of common engineering phenomenon, like strengths of materials cannot be negative, or at least if they are negative, it means the material is exploding or something like that. The shape of the distribution, because of this squared term in here, it has the same shape to the negative side as to the positive side, because the square gets rid of the negative term, and it's in fact symmetric about the mean, which is mu of x. Okay, so this is the usual picture, bell-shaped curve for the normal distribution, symmetric about the mean. So the mean is the balance point. It's the middle of the distribution, and it turns out that that balance point is also the mode and the median of this distribution. The standard deviation is the distance from the mean to the point of inflection, and if you recall, a point of inflection is the point where the curve stops curving this way and starts curving this way. In fact, it's a straight line at the point of inflection. We don't really need to know that for this course. It just gives us a sense of how wide this distribution is. Okay, so if we're told that a random variable has a normal distribution, then we just basically need to know two parameters. One is the mean and the other is the standard deviation. If we know those two parameters, we know everything there is to know about this distribution. I mentioned some of the properties. It's symmetric about the mean. The range is from minus infinity to plus infinity. The mean is the balance point, mu of x, and the variance is sigma x squared. So the standard deviation is sigma x. So one of the problems with the normal distribution is that the integral of this expression up here, so f of x, has no closed form solution. And what that means is that I can't find probabilities in a closed form way. The probability that x is less than or equal to, say, a would be the integral from minus infinity to a of f of x dx. And since this has no closed form solution, we're going to have to find that probability by integrating numerically. Okay, so we chop up our area up into little rectangles and add them up to figure out what the area is to the left of A. So basically, we can then produce a table of the CDFs, the cumulative distribution function values for the normal distribution. But the problem, of course, then is that we need a separate table for every possible mu x and sigma x. And so we'd end up with an infinite number of tables. Of course, we don't want to do that. That would be, of course, ridiculous. So what is the solution? Well, it turns out the solution is to standardize. And what I mean by that is we take our random variable x, subtract its mean, and divide by its standard deviation. And we call this z, and we call this the standard normal. Some properties of normal distributions is that linear combinations of normals remains normal. So if I have a linear sum of normally distributed random variables, or a normally distributed random variable times a constant plus a constant is still normally distributed. That means that this quantity x minus its mean divided by its standard deviation, this is x, which is normally distributed, minus a constant divided by a constant. This whole thing is still normally distributed. So basically z is normally distributed, and then all I need to know about z is what its mean and standard deviation is. Okay, so there we go. We need to find mu z and sigma z. First of all, mu of z is the expected value of z, and I take the equality here, what it is equal to, stick it in here, and take the expectation of that quantity. First of all, the constant 1 over sigma can come out front, and then I've got the expected value of x minus mu of x. This is the expectation of a sum, which we know is the sum of expectations. So I got 1 over sigma x, expected value of x minus mu of x. Well, of course, expected value of x is just mu of x, so this becomes mu of x minus mu of x, which is 0, okay? So this standardized random variable, z, has mean 0 regardless of what the true mean is of x, okay? So z will always have mean 0 after we standardize. The next step is to find the standard deviation of z, or we'll start with the variance, since our equations are in terms of variance. So sigma z squared is the variance of z, which is the variance of x minus mu of x over sigma x. We know for variances, constants can come out front, but we have to square them. So it becomes 1 over sigma x squared, variance of x minus mu of x. This is the variance of a sum, which becomes sum of the variances if these are independent. Well, mu of x is a constant, so it's independent of everything. So basically these two terms are independent. We get variance of x. Oh, I made a mistake here. It should be plus the variance of mu of x. Remember that constants are squared, and that minus 1 becomes plus 1. So this term here, this should be a plus sign here. Okay? Excuse me. But of course, the variance of mu of x is variance of a constant. Well, a constant has no variance, so that term is 0 and just disappears. Okay, so that means that we get, this boils down to sigma z squared is the variance of x, which we've ended up with here, divided by sigma x squared, which is, of course, just the variance of x. So I get variance of x divided by variance of x, which is 1. So this, when we standardize by subtracting the mean and dividing by the standard deviation, the quantity z, our standard normal, becomes normally distributed with mean 0 and unit variance. And that means that we can develop a table for z, and then we can use that to find probabilities for all other normally distributed random variables. In other words, we have a problem that looks like this. Here's our distribution with some mean mu of x and standard deviation sigma of x. We standardize it by subtracting mu of x. That basically shifts this distribution over to be centered on 0, and then divide by sigma x, and that basically collapses the distribution so that it has standard deviation 1. So we end up on the right-hand side with the standard normal distribution centered on 0, so mu of z is 0, and unit variance or standard deviation equal to 1. And then we can use this to compute probabilities as follows. Probability that x is less than or equal to some value a. First thing we do is standardize. So we subtract the mean, divide by the standard deviation on both sides of the equality. If I do the same thing on both sides, this probability is just equal to this probability. So I got x minus mu of x over sigma x is less than or equal to a minus mu of x over sigma x. And then this thing here is my z. So this becomes probably that z is less than or equal to this quantity here, a minus mu of x over sigma x. And then we're going to write this as capital phi of a minus mu of x over sigma x. And this is the phi is the standard deviation, or sorry, the cumulative distribution function of the standard normal. And they basically, there's a table in the summary pages, the first table in the summary pages, that gives us the standard cumulative distribution function of the standard normal. And we'll show you how to use that in later in this lecture, and certainly in our tutorials. Okay, so this is the illustration of what's happening here. The probability that x is less than or equal to a is this area to the left of a under the normal distribution. We standardize, that shifts this over and shrinks it or expands it so that the standard deviation is 1. And then the area we're looking for is the probability that z is less than a minus mu of x divided by sigma x, which is this area here. And those areas will be the same. Okay, so let's illustrate this with an example. Example 4.12. Let's suppose that it takes a certain probability professor's trip into work, takes t minutes. where t is normally distributed with a mean of 18 minutes and standard deviation of 4 minutes. What is the probability that it takes him more than 24 minutes to get into work on any given day? Yeah, this is a pre-COVID question where people actually still went into work. So we're given a couple of things here. We're told that the t is normally distributed, so I need to know its mean and standard deviation, and then I know everything there is to know about it. The mean is given to me as 18, and the standard deviation is 4. And so our distribution looks like this. Mean here at 18, standard deviation is 4, so I got a distribution that basically is bell-shaped, and I'm looking for here the probability that it takes more than 24 minutes to get in. That's the area under the curve beyond 24. So probably the t is greater than 24. Okay, so let's see how this works. Probably that t is greater than 24. If we're going to use this cumulative distribution function, we have to flip this around. So it's 1 minus probably that t is less than or equal to 24, and then my next step is to standardize. So I take t, subtract its mean, divided by its standard deviation, and then it's the same thing on the right-hand side. So I get 1 minus probability that t minus mu of t over sigma t is less than or equal to 24 minus mu of t over sigma t. And that first thing here is z. So there's our z there. And we know mu of t is 18 and sigma t is 4. So I know everything on the right-hand side. I get 1 minus probability that z is less than 1.5, which is 1 minus phi of 1.5. And then if we look in our summary pages, that is just equal to 1 minus 0.93319, which is 0.06681. And again, I'm showing more precision than I would normally show in a formal report. For example, I might show this to 2 significant digits in practice, because usually we don't know things like the mean and the standard deviation that accurately. In fact, we only have 1 significant digit for the standard deviation, so it probably makes more sense to just say this is approximately 0.07. I should show you how I go from this step to this number, and for that I'm going to dig out the summary pages. So let me just pause this for a minute, and then we'll resume. So I've opened this Wikipedia annotator. This is my summary pages. And if I scroll down here, you'll see some stuff that you recognize. Our sequence of formula on the first page, common distributions, second page. Then we get into some stuff that we're going to see in a couple of weeks. This is statistical stuff. This one is about confidence intervals. And then this one here is about hypothesis testing. And then we start in on the normal distribution. Now the normal distribution, this is the standard normal, by the way. So the normal distribution looks like this. Standard normal, by the way. Oops. Let me try that again. Okay, so we got standard normal, looks like this. And centered on 0. This is fz of z. So this axis is z. And basically we're looking for, okay, so this this table gives me, if this is 0 here, gives me everything to the left of the point we're looking at. So we know that this one here is 0.5. So when we have 0.00, so that's the way we read this. This is 0.00. Okay? The area to the left is 0.5. We're looking in our problem at 1.50, which is this number here. Okay? So 1.50 is here. Oops. No. It'll be out here somewhere. And that'll be, let me throw this in a different color. Let's just try that again. Let's show this in green. Sorry, people who are colorblind, but I'll put it the other way around as well. So that's this area. And that's 0.93319. Okay? So that's how this table is used. Because it only looks at values of z above 0, or 0 and above, you have to use symmetry if you're looking for probabilities that are less than 0. Okay? And that you'll notice that this point here, so this value here is 1.50, this is 1.51, 1.52, 1.53, 1.54. The other thing to note here is that these little superscripts down here, this means 0.999. Okay, so I wanted to not waste space on nines in these tables. You can see when we get down here, there's 4 nines, 7327, and this is sort of explained down at the bottom. Okay, so we didn't waste a bunch of space in the table on nines. So if we need a number, if we need 1.56, for example, we have to go to the second page. So 1.56 is this number here, 0.94062. Okay? Okay, so let's get out of this and return to our normal distribution, to our discussion about the normal. So that's basically where this 0.93319 comes from. Problems with this model, I mentioned before, the normal distribution, the range is minus infinity to plus infinity. So this model allows some probability of arriving at work before leaving. We know that that doesn't happen in practice, so there must be something intrinsically wrong with this model as a model of travel time. In fact, if we look at the probability that t is less than 0, so that we arrive before we leave, I do my usual thing, standardize, and I get on the right-hand side 0 minus mu of t over sigma of t. And that's 0 minus 18 over 4, which is phi of minus 4.5. And basically, if we look at phi of minus 4.5, that's the probability that I'm less than minus 4.5 over here. That's the same as the probability that I'm greater than 4.5 on this side. This is my standard normal curve due to symmetry. So probably phi being less than minus 4.5 is going to be equal to 1 minus phi of 4.5. So 1 minus the area to the left of 4.5 gives me area to the right of 4.5. If we look at our summary pages, if I go back to that, we see, where's the summary pages? We see that the largest value we have is 4. So in fact it's over here. Oh no, it's right here. This is 4.09. And 4.09 is 0.99997843. And I think I've got that over here. Okay, I used it just 4.0, so that's close enough. Let me go back and show you. So 4.0 is 0.997439. No, that's this. 4.0 is this 0th column here, 0.9996832. Okay, so we know that probably that z is less than 4, which is around here. Let me just go back to full size. So 4 is around here. By the way, these are actually farther out to the right than I'm showing, but I just show them this way. And the area to the left of 4 is 0.9996832. And that means that probably that z is bigger than 4 is this 0.00032 term, 4 zeros 32, and therefore probably that z is less than minus 4.5 is going to be less than 0.000032. Okay, so this model gives a very small probability of arriving before we leave. Nevertheless, this is non-zero. So, and in all of our years of history, we've never seen somebody arriving before they leave. So, so we know that this is probably wrong. I say probably because we don't know for sure. We haven't looked for all of time, but but it suggests that we should use a non-negative model for travel time. And we're going to look at one shortly called the log normal distribution. Okay, the other thing that I mentioned earlier on is that the normal distribution is popular because of something called the central limit theorem. And the central limit theorem says that sums of random variables will tend to a normal distribution. And this is very useful because in engineering we're very often dealing with sums. Let's illustrate this using Bernoulli trials. If I think about a single flip of a fair coin, let's suppose P is equal to 0.5, that's a fair coin. Then our distribution looks like this. We got two bars, one at 0 and one at 1. So 50% probability of getting a 0, which would be a tail, and probability of getting a 1 is also 50%. This is about as far away from a normal distribution as you could possibly imagine. It doesn't look anything like a normal distribution. However, let's take a look at what happens when we add two of these random variables, x1 plus x2. So this is the number of heads in two tosses, for example. We know that the probability distribution of that, the probability of getting no heads is the probability of getting a tail, and that's a half times a half, which is a quarter. Probability of getting one head is either a tail and a tail and a head, or a head and a tail. And we know that that's going to be a half times a half plus a half times a half, which is add them up, we get a half altogether. And then the probability of getting two heads is going to be a quarter. And we've already seen this several times in this course. If I draw that picture, I've got a quarter here, a half here, and a quarter here, and already I'm starting to see a bell shape coming out of this picture. So we can see even when we've added two terms, we're already starting to look vaguely normally distributed. If I continue this on and look at sums of random variables, when we get up to sum of 6 random variables, it's starting to look pretty normally distributed. And in fact, it gets more and more normally distributed as n gets bigger and bigger. Okay, let's look at another example. Example 4.13. Tensile strength of paper is modeled using a normal distribution with mean 35 pounds per square inch and standard deviation 2 pounds per square inch. I could jump right to where are there any problems with modeling tensile strength using normal distribution? Again, since the normal allows negative values, then it's allowing some probability of this tensile strength of the paper being negative, and I assume that just means the paper explodes or something like that. And we don't see that in practice, so that can't be right. On the other hand, the mean is 35 and standard deviation is 2, so the negative values are 35 divided by 2, so about 17 standard deviations away from the mean, which is a long way away in normal space. So this is actually probably a pretty reasonable distribution. So I'm asking some questions. What is the probability that the strength of a sample is less than 40 pounds per square inch? And then approximately 10% of all samples have a tensile strength stronger than what value? Okay. So let's define the random variable x to be the tensile strength of paper, and we're told then its mean is 35 and its standard deviation is 2. So the coefficient of variation is fairly small. This is, I would say this is a not very random process. The coefficient of variation is only 6%. So we're looking for, in part A, the probability, part 1, the probability that x is less than 40. This x, we're told, is normally distributed. So our first step is to standardize. So we subtract the mean, divide by standard deviation on both sides of the equation. So we got here, this is z. We know the mean and standard deviation on the right-hand side, so we got 40 minus 35 over 2, and now we end up with 2.5. And then basically this is the cumulative distribution function. If we go back to our summary pages and look at this, we're looking at 2.50, so that's this number, 2.5, and the 0 is up here. Is 0.993790. Let's just check and see if that's what we got. 0.993790, yes. Okay. So that answers part 1 of this question. Part 2 of the question says approximately 10% of all samples have a tensile strength stronger than what value? And basically it's saying if I were to repeat this experiment many times, what tensile strength is exceeded only 10% of the time. Okay, So I'm going to call this x sub 0.10. And basically we know that value will have area above it of 0.10, 10%. Okay. So I want to find this x 0.10 such that the probability that x is bigger than that value is equal to this 10%. Or alternatively, x less than x 0.10 is 0.90. And that this value we can get from the cumulative distribution function and from the table. So basically we know that this is normally distributed, so our first step is to standardize, subtract the mean and divide by the standard deviation on both sides of the equation. So I'm looking for the value of phi, x 0.10 minus, oops, sure, that should be minus the mean. Oh, let me just go back and make this full screen. Minus, so that should be minus. Okay, so that I want to find the quantity that should go in here such that phi is equal to 0.90. So what that means is that I go back to my summary pages. I'll make this big again. What I'm going to do now is I'm going to scan through these summary pages for a value in here that's as close as possible to 0.900000. I see here I've got 0.903, 0.904, 0.906. This one is 0.89, so it suggests that I'm going to get closer to 0.900 on the next page, where I've got, so this one is let's say it's 1.26 or 27 or something like that. So let's go to the next page. 1.2 is 0.89, 0.896, 0.898, 0.899, 0.901. So it's going to be somewhere between these two. So 1.28, let's suggest 1.285. Let me just write that down. 1.285 would be my guess at the value there. Let's see what we used in the solution. Okay, 0.9, so now just need to find, okay, so I saw 1.2, that less than 1.28 was 0.89, let's go back out here, 0.89972, and less than 0.29 is 0.90147, and so I just guesstimated somewhere in between is 1.285. By the way, don't bother with detailed linear interpolations. Again, we usually don't know our parameters that closely enough to warrant that, so I usually just guesstimate the numbers in between. So I'm guesstimating that Z is less than 1.285, less than or equal to, doesn't matter. 1.285 is the value that I'm looking for. Okay, so that means that this number here must be equal to 1.285. Okay, and if I set that equality and solve for x 0.10, I get x 0.10 is mu x plus 1.285 times sigma x, and that gives me 37.57. Now, I should point out a little trick. If you're doing these inverse problems where you're trying to find a value of z that corresponds to a certain probability, it's much easier to do this using the last line of the t-distribution table. We haven't talked about the t-distribution table yet, but we will do so shortly. If I go back out and look at my summary pages, the table after the normal distribution is the t-distribution table. And we'll talk about that shortly, but it turns out that the very last line of this t-distribution table corresponds to the standard normal. So what that means, and by the way, this t-distribution table is already an inverse table. So we go into it with a probability to the right. So that's another confusing thing. The normal distribution is table gives me probabilities to the left. T-distribution and chi-squared that we're going to see next give me area to the right. Okay, so just bear that in mind. So if I'm looking for a point with area to the right of 0.10 in the standard normal distribution, I go right to the bottom of this column. I see 1.282. We had guessed 1.285. This one gives us a more accurate result, and probably you would have got more closer to this if you had used linear interpolation. But this last line is a much faster way of finding that than searching through the other table for a value close to 0.9. So let me go back out to my solution. Yes, okay. If I put the 1.282 in here instead of the 1.285, I see that this changes a little bit, but very little. Okay, so that's not enough of a change to make any difference. Okay, so basically all I'm saying is that if you've got this sort of problem, just go to the last line of the t-distribution table and use that to the number that you see there. Okay, so back to normal approximations to sums of random variables. This is again back to this idea of central limit theorem, and we can use that to approximate probabilities relating to sums. For example, we saw earlier the binomial distribution is the sum of a series of Bernoulli trials, I equals 1 to n of xi, and suppose we want to find the probability that n900 is greater than 495. Strictly speaking, this particular term would be the probability that n900 is 496, plus the probability that n900 is 497, plus ... up to n900 is 900. Well, not only that, not only are each of these a very difficult probability computation, there are also 405 terms in this sum, and they all involve 900 factorial, and that is a difficult thing to compute. You're going to have to use some sort of approximations to figure out what those, this would be 900 choose 496, what that is. And then you've got p to the 900, so exceedingly small numbers and large numbers. But if this quantity, I equals 1 to 900, is approximately normally distributed, and will be because n is very large, then all we need to know is what is the mean and standard deviation of this, and then treat it as if it's normally distributed. Well, the mean we know is just n times p, and the standard deviation is the square root of npq. So we can approximate the probability that n sub n is greater than 495 is approximately equal to 1 minus, we've got to flip this around to use the CDF, phi of 495 minus the mean divided by the standard deviation, which is going to be 1 minus phi of 495 times minus np divided by square root of npq. I should point out that in some of the solutions that you'll see in this course, they employ for the binomial distribution, because binomial is discrete. It employs a half-interval correction. Now, if we're approximating a continuous random variable with the sum of continuous random variables with the normal distribution, we don't have to do this half-interval correction. And in fact, I'm suggesting that you don't bother with it anywhere. But if you do see it, that's where it's coming from. The probability that n sub n is greater than 495 is actually more closely approximated by n sub n is greater than 495.5. And so we have that half-interval correction in there when we go into the normal distribution tables. And like I said, let's not worry about that, but if you see it, that's where it's coming from. Let's look at this particular problem. A fair coin is tossed 900 times. Fair coin means that our probability of success, heads or tails, is 0.5. And then the question is, what is the probability that more than 495 heads turn up? So this is the sum of 900 Bernoulli trials, and we're going to assume that that's very closely approximately normally distributed, which it will be. We don't want to add up the 405 terms. Not only that, it's difficult to compute these very large factorials. I should point out that generally the normal approximation is considered good if n is greater than 30, and often in my experience it's good even if n is greater than 5. Okay, so we're going to assume it's normally distributed. We need its mean and standard deviation. If p is equal to 0.5, then the mean is np, which is going to be 450. And then the standard deviation is square root of npq, which turns out to be the square root of 225, which is 15. Okay, so we get a mean of 450, standard deviation of 15. So probability that n900 is greater than 495 is then approximately equal to 1 minus phi of 495 minus its mean divided by its standard deviation, which is 495 minus 450 over 15, which is 1 minus phi of 3.0. And then I go into my summary pages, look up 3.0, I see 0.99865, subtract that from 1, and I get my answer 0.00135. We could check to see how the half interval improved approximation works. So I'm taking here phi of 495.5 minus 450 over 15. That gives me a slightly different value in the CDF, 3.03, and changes my probably a little tiny bit from 0.00135 to 0.00122. And in fact, according to Mathica, the exact, and I put exact in quotes here because I don't really know how exact it is. They've done some sort of calculation, and I don't know how accurate it is, but it came out to 0.00120. So it looks like this thing is a little bit more accurate than this thing, but they're all pretty close. Okay, and that concludes then week 7, lecture 1, and that's it for the first lecture. Okay, so I'm going to pause.